Is starting YouTube the same as starting recording for this for meeting?
Do we record as well? Because it's on YouTube.
We sometimes do. So I mean,
and maybe you can.
Harin, do I also need to record or no?
Why not?
You can. So you'll have a local copy, but it should be anyways on the
YouTube, yeah. So,
but you see, Marietta, your copy, you are the owner of this copy. There, it's YouTube is the owner.
That's true, yeah. So, Rafe, do you mind if I record?
No, that's absolutely fine. Yeah.
Okay, then let's press that button as well. So, and then we can start. Then, Delio, I will ask you to introduce the speaker.
Good afternoon, everybody. Welcome to our 5th Lumer lecture. So after previous lectures by Marcel Filoche, Wolfgang Arendt, Laurent de Villette, Enrique Sozois, this day it's Rafe Mazzeo's turn. So I'm very, very glad that Rafe accepted our invitation to our Lumer lecture. I will say a few words about his background for those of you who are not familiar with this topic. So Rafe Mazzeo got his PhD in 1986 at the MIT, and he moved right away to Stanford, where he's been essentially since 1986, apart from a brief leave, which is spent at the University of Washington, Washington University. Rafe has a large number of publications, over 110, according to Central Blood, and probably more, about very different topics, including elliptic theory of differential operators, differential geometry of complete spaces, where there's in totally constant curvature, Hodge cohomology, Keller-Einstein matrix, conical matrix in Riemannian surfaces, and what's maybe closer to our own interest, also some very relevant work about diffusion and operator theory, including Harnack inequalities and heat kernel estimates, Fried-Landry inequalities, and Dirichlet-Neumann operators. He has also written a book about general diffusion and its interplay with population dynamics. So as you see, it's a very, very, very large and broad spectrum of interests. He's got several awards, including NSF and Sloan Research Fellowships. He's been in the editorial board of Nappe Poincaré Nonlinear and Communication PDs. So you have certainly got him the feeling of how how broad the interests and the achievements of Rafe Mazzeo are. So I'm very happy to have him here, and please, Rafe, the stage is yours.
Thank you very much, Delio. So it's a real pleasure and a real honor to be invited to give this lecture. And I just wanted to say a few words. I'd known the name Lumer, and I looked up about him, and I found that we have actually sort of many points of, well, not quite contact, but near contact. And in fact, this famous theorem of his with Ralph Phillips was done here at Stanford, 60 years ago. And I want to sort of highlight in particular, his relationship to Ralph Phillips, because Phillips was, of course, this, amazing mathematician who was an extraordinarily influential person to me early in my career. He was probably the reason I got my job at Stanford, because I'd done some work that was relevant to things that he and Peter Sarnak were working on at that time. And I interacted with Ralph a lot during my first 10 years at Stanford before he passed away. He was a wonderful mathematician, and he was very supportive of the community and young mathematicians, and I really owe him a lot in my career. And then I was at, in fact, University of Washington, not Washington University, which is a completely different place. But I was at University of Washington for a couple of years, where, in fact, Lumer had also spent apparently a decade or more. So in any case, so it's a real honor for me to give these lectures. So the theme I want to talk about today is broadly construed. It's about the analysis on singular spaces, and in a very particular context, which I'll get to in just a moment. So when Delio was very kindly listing my various works in various directions, when I look at it, I always think, well, it's about the same thing. It's all about analysis on different types of singular spaces, and there's a lot of applications. And I think that if it looks broad, it's only because people have been thinking about doing analysis on, manifolds or domains or things, and that's an ancient thread. And if you look at spaces which are somehow mildly singular in a rather structured way, which I'll describe in a few moments, these are just as natural as smooth manifolds or domains with smooth boundaries. And they arise in many different contexts. There are many problems out of applied math, out of geometry, out of physics, many places where these appear. And my philosophy for many years has been that one just needs to develop the right analytic tools. So whether it's elliptic, parabolic, or hyperbolic theory, for example, to study PDE on these spaces. And as you all know, and there are many great experts in this audience, there's a broad range of tools ranging from very let's say general tools coming from operator theory or coming from let's say geometric measure theory, for example, things like this, various notions of weak convergence. And then there's sort of, I want to say stronger PD tools. I don't mean stronger in terms of effective, but, they're really point-wise, just as, one moves from like distribution theory to really point-wise fine regularity estimates. And that's kind of the transition that I'm interested in making. Okay, so I'm going to start. And what I'll be talking about is the geometric flow of networks. Now, again, this is a subject I've done some work in, and I think that I will try to mention a number of names of people who have contributed, and there may well be people in the audience who are far more expert in this than I, and there are many different aspects of it. But I'll try to sort of steer a line towards what I've in particular been thinking about. But the general theme, and again, since this is not necessarily a geometric audience, which is my natural milieu, I just want to say a little bit about, from my point of view, why these problems have become important. So, so one can use parabolic equations to smooth out various things, smooth out functions, smooth out geometric objects, and so on. And there are a lot of motivations for studying these geometric flows. So, there's a whole field now called, geometric flows or geometric evolution equations and so on, where one is using sort of various geometric features to take an object and sort of make it sort of more regular, smoother, and so on. And as I say, there's sort of a number of reasons or a number of motivations for doing so. One of which is the classification problem. If you have an object and you don't know much about it, if you can sort of make it look more regular, you might be able to understand what it is. Now, for simple things, well, we know what it is to start off with, but in higher dimensional manifolds, that is a real mystery, and I'll mention that in just a second. And secondly, it's a very constructive method for sort of taking something and improving it. And, these sorts of applications come out throughout applied mathematics of sort of shape optimization and so on. But an example of classification was this famous theorem of Poincare, the Poincare conjecture, proved almost 20 years ago now by Perelman, where a geometric evolution equation on three-dimensional manifolds was used to solve one of the most famous open problems in topology. That if you start with a closed three-dimensional manifold and all you know about it is that it's simply connected, that in fact it has to be diffeomorphic to the sphere. And what the proof was, as many of you presumably know, is that you start with an arbitrary metric, an arbitrary shape of a three-dimensional manifold, and then you gradually improve it using this evolution equation. And well, the idealized version is it gradually gets rounder and rounder, and at the end of the day, it's a sphere. But why simple connectedness, simple connectivity is what ensures that, and what kind of analytic disasters can happen along the way made this an extremely subtle and difficult problem. But this was a great hallmark in the application of PDE to geometry and topology. And of course, these flows can often be interpreted as gradient flows in an infinite dimensional space of all geometric shapes. So that's kind of the broader context in which one wants to think about these things. And this is where it interfaces with, abstract things like semigroup theory and so on. And of course, there are many physical or biological or chemical processes which are modeled by these sorts of flows. And I'll mention very briefly some of those. This could have easily been another talk sort of talking about those sorts of applications. Okay, so the example I want to talk about today is what's called the curve shortening flow. And again, this is a fairly familiar topic, and many of you may have seen this, so forgive me for being rather elementary for the first 10 or 15 minutes, but I just want to describe this in slightly painful detail before we get to the main points. So the curve shortening flow is a gradient flow for the length of a curve. I don't write that out explicitly below, but if you just write the length of a curve in terms of its parameterization, you take the gradient of that in the space of all curves, and you wind up with this flow. But from a purely geometric point of view, what you're doing is you start with a curve, and you're trying to sort of make it sort of rounder, make it, you try to sort of push in the bits which are very curved, and then you, the parts which are not very curved, you try to move them out. So in this case, we're looking for a family of curves, parameterized curves, gamma of t and x, and we demand that the velocity, that how the curve is changing at each point, is proportional to the curvature at that point. And I have a bad feeling I had a nice picture before where I, oh, you know what I can do? Hold on for just 2 seconds. Now, oops. Yes, that's what I want to do here. So I want to go here. Yeah, so I can do something here, and then we go backwards. Okay, there we go. So with this thing, if I have, any place which is very curved like this, I can sort of push it inwards fast. Regions here which are curving the other way, I sort of push out the other direction, and regions which are pretty flat aren't changing very much. Okay, so that's kind of the general philosophy. And sorry, I had a better illustration of that, which I seem to have omitted from these slides. So, okay, so there's an equation almost, and finally when we, okay, I did have it, forgive me. I was forgetting. So you can see here that we have this curve pushing in various directions, and it pushes either outwards or inwards, depending whether it's curved positively. And as you can see of this evolution of the curve, it starts off very bumpy. It somehow becomes less bumpy as you move along. It eventually becomes convex. It's getting smaller all the while, because remember, we're following the gradient flow of length, so we're expecting length to decrease. And gradually it shrinks to a point in finite time. So there's finite time extinction for this flow. Okay, so this is an incredibly heavily studied thing. This goes back to the 80s with Gage and Hamilton and Grayson, where they sort of established this fully, that you start off, I mean, the remarkable theorem is you start off with an absolutely general closed curve. Let's suppose it's a little bit smooth, but let's say C1, I don't know what the threshold of regularity is. You start off with an arbitrary Jordan curve that's minimally smooth, and it instantaneously becomes C infinity. It gradually straightens itself out. It never crosses itself, which is kind of the miracle. And it becomes convex, and then it slowly shrinks to a point. Okay, so that's a nice model case. I mean, it's maybe not the most significant geometric theorem in the world, because you knew it was just a closed curve anyway, so it doesn't help with classification. Actually, this does have a topological application. If you're interested in the topology of the space of all embeddings of curves, it actually shows you that that space is connected in a rather interesting way. So this has interesting applications to the topology of the space of all diffeomorphisms of the disk, and so on. But in any case, so this was understood 40 years ago. Let me just mention a couple of other sort of famous geometric flows, again, all very well known. One is flowing a two-dimensional surface in R3, where instead of the curvature of a curve, I replace that by the mean curvature of the surface. Or there's, hundreds or thousands of other papers where you look at other variants, you look at 1 over the mean curvature or the Gauss curvature, or various curvature quantities, and you're sort of trying to reduce the surface or straighten it out, where the driving force, the velocity at each point, is given by some curvature. So each of these have different uses. They've had different applications, and they present different analytic challenges. So there's a lot of literature on this. For abstract objects, Riemannian manifolds, there's this Ricci flow that was applied to the Poincare conjecture, for example. And then there's sort of a quantized version that has applications to, metallurgy or superconductivity or various other things, the Allen-Kahn flow, which is that I look at a scalar function. So I take a double well potential, W of u equals 1 minus u squared quantity squared. And I take the flow associated to that. I hope I have the sign right. That's supposed to be a plus 1 over u, 1 over epsilon w prime of u. Could have gotten that wrong. But I take a flow where I have a small parameter epsilon, so it's essentially a semi-classical parameter. And what happens here is that there's a one-dimensional solution, which is, as epsilon is very small, it concentrates along x equals 0. So it's making a transition from -1 to +1 with a sort of a short interface over a width of the length epsilon, essentially. So it's on either side of that interface, it's looking very close to -1 or very close to +1, then it's making this interface. And one can look for more general curved analogs of these. So I've drawn a picture of a domain. This is sort of the general round shape. I look for solutions of this equation that are concentrating along some curve. And I'll just say it, I didn't write it sort of in particular, but I can find either stationary solutions where du dt is 0. And then what's happening is that this interface, when epsilon is very small, this sort of jumping region or the vortex set or the interface region is very close to a geodesic, or in general, a minimal surface in higher dimensions. And for the flow aversion, and let's just think of 2 dimensions, and I take the flow, the parabolic version of this, what you see is the interface is sort of changing, and it's changing exactly by this curvature flow to leading order. Okay, so there's very close connections to this purely geometric problem I talked about before. So I may come back to some of these later, but I want to focus now on a different aspect of this problem, which was we have this general notion of flow by curvature. And now I'm interested in what happens if your initial object is singular. And again, I'm trying to be clear that there are things which are singular, which are kind of just smooth things which happen to be kind of rough. So it's like you take a Lipschitz graph, or you take something that's not very smooth, but it still looks manifold-like. And that's a different phenomenon. That's sort of the parabolic regularization. How do you start off from rough initial data and it gradually becomes, or instantaneously becomes smoother? I'm interested in things which are genuinely not manifolds. So networks are one example, but I list a few other natural applications where I have a manifold with corners. I have foams of surfaces, so sort of surfaces intersecting in various systems of curves and points in space and so on. So as, for example, a cluster of bubbles will have sort of very complicated sort of interface structure. So various things like this are what I'm interested in. So here are some examples. So the first is network of curves. So I'm thinking about a set of embedded curve segments that when they intersect at vertices. So there'll be outer vertices where the network may be sort of fixed, and then interior vertices that are whose locations are not fixed, but I'm requiring the curves to sort of be stuck at a given point. I can think of the 2-dimensional version of this in 3 dimensions of what I call foams of surfaces. So I have various sheets coming together in various ways, and as you can see, I'm not a very good artist, so I tried to do the best I could.
Ya valla şey vardı, bir makale vardı onu.
Oops, forgive me. Thank you. Okay, so I'm not a particularly good artist, but you can hopefully get some sense of, and just think of sort of a big cluster of bubbles where things come together. In all of these cases, one knows from sort of both physical experience and theoretical arguments that sort of the stable kind of configurations are where curves come together in a finally a fairly minimally singular way. So for example, only 3 curves come together at a point with a network. Or with surfaces, I might have 3 different surfaces meeting in a line, a curve, right, meeting at equal angles. Or there's another stable configuration, which I will maybe talk a little bit about later, where I have 6 different surfaces meeting at a point, but then they meet in triples along things. So this is like a cone over a tetrahedron. So this is sort of another standard type of singularity when you have a cluster of bubbles, for example. Okay, here are other more complicated shapes. So when I talk about a surface with conic points, so I have some sort of 2-dimensional surface, but it has pointy bits, or it can have not just a single vertex, but it can have a whole edge. So again, my drawing is not maybe the best, but you can imagine sort of something with a conic edge in R3. And all of these things generalize in higher dimensions. So to give you a sense of the types of singular objects that they may sound a bit outlandish, but when there are many interesting applications for these, you can start off with, let's say, for example, a Well, let's think about the inductive procedure. Start off with something nice and smooth, like a circle or a closed surface or something, and then you take a cone over it. So you now have developed a singularity. Maybe you do something a little bit more complicated. So you take up a cone cross Euclidean space. So now you have an edge. So the conic vertex is sort of spread out along a higher dimensional thing. Okay, so now I have a space with a singularity. Now let's take a cone over that, right? And maybe, and then cross that with the Euclidean space. And now I have a space with sort of an iterated singularity. Then I can take a cone over that, and I can do that 500 times. So there's sort of a certain hierarchy of types of singularities. And in geometry and topology, and actually in many physical applications, these types of stratified spaces are not uncommon. So again, my sort of broad theme is, how do you do analysis on these? How do you do PDE on these? Okay, so finally, let's get back to the curvature flow. And I have a network of curves. I call my initial network gamma naught, and there's a collection of curves, and they have various rules. So in particular, they're all, let's say, smooth. I'm not too concerned about the regularity of the individual curves because, again, we know that they smooth out immediately when we start flowing. But what's important is that they meet at vertices. They can meet several at a time, and they don't cross each other in their interiors. And one other type of exotic behavior that one might want to rule out is that we don't have two curves coming together in tangent at a vertex. So they when they meet, they're meeting sort of with a positive angle. Okay, and then you let each of these curves evolve by the curvature flow, so this gradient of length. And that's sort of a system of equations. And I'm not telling you quite yet what's going to happen to the vertices. That's on the next slide. And the only thing I wanted to mention is that even in the case where there's a single curve and not a network of curves, this equation conceals the fact that there are two separate things going on. One is the curve is sort of moving as a geometric object perpendicular to itself. And the other is that it can be moving along itself. There can be a tangential part of the flow, and that corresponds to a change of parameterization. And so, in fact, I could add to this equation, I could add a term that's some other function times the tangent vector of the curve, and it would give me something that was geometrically indistinguishable. It would look like the same curves, it's just that their parameterization is changing in different ways. So, in fact, I've written down the equation that we're going to use, which is kind of a one standard normalization or choice of this. So I take just the second derivative with respect to x. That is a vector that need not be perpendicular to the curve, right? That's pointing off, depending on the parameterization. If x is not an arc length parameter, it's not pointing perpendicular to the curve. It has some tangential component. But this really exhibits that this is a parabolic equation, in a nonlinear parabolic equation. So I have this 1 over mod gamma prime squared as a coefficient. Okay, so here we are. We have now we're in purely PDE world. We have a nice nonlinear parabolic equation, and we'd like to understand what happens. And as I said, we need to understand what happens at the vertices. So at the vertices, we have a couple of requirements. Now I've drawn a network here where I have 3 curves meeting at a point, but in fact I could have any number of curves meeting at a point in this network, and that'll actually be an interesting case that we'll talk about in just a moment. And so you have 2 conditions. They're boundary conditions. One is that that the curves all intersect at that point. So I'm thinking of x equals 0 on each curve as being that end where you're meeting that vertex. So that's the first condition, that at x equals 0 for all values of t, they intersect at that point. But the point itself could move, of course. And then the Herring condition is saying that the sum of the unit tangents at the intersection point adds up to 0. So this is some sort of stability condition. Okay, so these 2 conditions together are the boundary conditions. And so together I have a system of parabolic PDEs. I have this system of, I have this system of equations. So for every curve, I have this nonlinear PDE flowing on it. And I have this set of boundary conditions. So now that's a problem that's not phrased weakly. It's phrased as just a classical parabolic boundary problem.
I'm sorry, can I ask a question?
Mm-hmm.
So,
please.
So this second condition about the derivatives, this means that the angle is, in your case, the angle is 2 pi over 3.
Well, so when you have 3 curves, that's what it means.
Exactly. Mm-hmm.
But if you have 18 curves, then
it's
balanced. That's exactly right. But yeah, and I should have said that explicitly. When there are only 3 curves, it means they intersect at angle 2 pi over 3.
Okay.
Thank you for clarifying that. And I think I said that here. So, so when I say the stable configurations, these are the ones that in some sense you expect to be generically true, that you only have 3 curves intersecting at a point. And they meet at angle 2 pi over 3. And I call these regular vertices. Okay, other intersections I'm going to call irregular. And when you flow, you expect that generic behavior predominates. So namely, you're going to see most of the time, you're just going to see at later stages of the evolution, just 3 curves meeting at a point, but there may be exceptional values of time where more points come together. Okay. So, and so I want to illustrate that sometimes irregular ones are unavoidable. So this is actually a movie. So this is pulled off of Ken Bracke's webpage. This is quite a famous movie that many of you may have seen, which is that you have a complicated network of curves. He developed, so Ken Bracke was a student of Almgren's back in the 60s and 70s, I think in the 60s. And he developed a lot of computer software, and he developed a very important theoretical tool, which is known as the Bracke flow. It's a varifold flow for studying these things. And so let's see if this works. Yes, there we go. I think, okay, there we go. So there's a movie. So this is just pulled off his webpage. But so here's a network which is evolving. And you can see various features, like each of these regions is getting smaller. And if you observe, you see edges shrinking. And most of the intersections are threefold, or these trivalent vertices. But every once in a while, there'll be an instance of time where you have sort of a higher valence vertex appearing. So it's a lovely movie. And of course, it's just a numerical simulation, but the goal is to show that this is really the, you know, the general behavior that somehow you move towards a smaller object. Now, one of the things we'll be talking about a little bit later, what are the final states of such objects? But here it's just sort of gradually evolving to something that's looking simpler and simpler with fewer cells. And you see the types of configurations and the way that certain regions can shrink off. So analytically, this is a bit subtle, but here we are. And what is this final object? Well, it's a network of straight lines. So the fact that it's a stationary thing means that the curves have to be minimizers for length, or stationary points for length. They're straight lines, and they meet in these regular trivalent vertices. So this is a Steiner tree. So it evolves eventually to a Steiner tree. Okay, so let's get back to the analytic side of things. So the boundary conditions satisfy the Lopatinsky-Shapiro conditions. So these famous conditions which tell you that a problem is kind of well posed at the boundary. You have to set it up the right way. So you're not thinking of it as sort of that, well, let's say, even though it looks like a bunch of different equations on different curves, you can sort of pile it all up as sort of a big vector valued system on one curve. So that's one way to reframe it. But in any case, these boundary conditions satisfy the regularity conditions. And as I just mentioned, there is a very weak formulation of this type of setup, which actually applies much more generally, that was developed by Bracke in the 70s, which is using the language of varifolds, so generalized curves and surfaces. And what's nice about this Bracke flow is that you can apply it to almost anything, right? So you can start off with kind of a very general geometric object and you can flow it. The disadvantage is you have no idea what happens. You just know that the flow exists. It needn't be unique. All sorts of horrible things can happen. And let me just give a standard example. This is actually not a real worry for one-dimensional curves, but this certainly happens in various other configurations where you start off with something that's, let's say, one-dimensional, and instantaneously it fattens up to something that's two-dimensional. So there's plenty of examples of this happening with the Bracke flow. So, you know, this is governed by the sort of the weak convergence, but from a PDE point of view, this is very undesirable. So in any case, I just mentioned this, and I'm not to say that that's not a very useful and interesting point of view, but I'm just steering a different path. So as I said, I'm very interested in strong solutions, namely things which are really classical solutions of this PDE. Okay, so people have studied this network flow going way back. 30 years ago now, Bronsart and Reidig wrote a much cited paper where they, this was really kind of almost an applied paper where they were looking at sort of formal asymptotic methods and kind of predicting what would happen. It's a very lovely paper full of good ideas. And they actually, you know, gave convincing arguments for the short time existence. But, and here's kind of an interesting thing that relates to sort of the interface between abstract and specific PDE theory. they needed a set of compatibility conditions at the vertices. So I've told you what the boundary conditions are, but the reality is that those aren't quite enough. And I wanted to say a couple of words about this because this is kind of a weird sidelight on something that people don't often think about, which is the following. Suppose that you have just the one-dimensional heat equation on an interval, right? And you have, so just linear heat equation, nothing could be simpler. And you have initial conditions at time 0, and then you have side boundaries at x equals 0 and x equals 1, and you have functions phi naught and phi 1 at these side boundaries. Okay, and let's suppose that u naught, phi naught, and phi 1 are all smooth functions, right? So you expect solutions to the heat equation are smooth. That's obviously true when you're in the interior, when x is strictly between 0 and 1 and t is strictly positive. And well-known theorems tell you you're actually smooth up to x equals 0 or x equals 1 when t is positive. You're smooth down to t equals 0, but at the corners, there are problems. And again, this is something that you may have seen once and forgotten about because it doesn't seem very significant, but in fact, from certain points of view, it's very significant that if I start with very regular data, and let's suppose I could even let phi naught and phi 1 be 0, but I start off with a smooth function that's non-vanishing at the corners, you expect something kind of horrible to happen right at the corners because it can't be continuous. It's supposed to be 0 coming down from the sides, but it's non-zero coming along the bottom. So compatibility says that the function and all of its derivatives match up in a certain way according to the relationship of the PDE so that it actually can be smooth at the corner. Okay, well, this doesn't seem very important, but of course, if you're trying to think of this as a flow in some function space, it's actually saying that the semigroup is not strongly continuous. It says that, you may start off with C infinity initial data and, it jumps to something C infinity, but the convergence is not in C infinity. It's in a much lower space. And that's kind of at the heart of a lot of technical issues when you try to apply abstract theory, that if you don't have these compatibility conditions satisfied, you don't have a strongly continuous semigroup. Okay, well, here's kind of a weird sidelight on this, and this is kind of informed by my microlocal background of if something doesn't look smooth, you can make it smooth by a process of resolution or blow up. So what I want to do here is kind of an odd process, if you're not used to this sort of thing, which is I want to introduce polar coordinates at each corner. And I do this respecting the parabolic nature, the fact that t and x are kind of scaling differently, as is usual in heat equations. So I introduce these polar coordinates r and theta at each corner, where root t is r sine theta and x is r cosine theta. And so think about polar coordinates. If I introduce them, I can sort of take the face r equals 0 as a literal geometric feature. So, I'm sort of introducing singular coordinates, but then I'm putting the r equals 0 face as a new geometric face, a new boundary. Okay, so I can do that. It's just kind of a change of notation. You can think of this just introducing singular coordinates. And the fact, and it's not completely trivial to prove, in fact, and it's kind of a weird perspective, is that any solution to the heat equation, if u naught, phi naught, and phi naught are all C infinity, then the solution lifts up to this space and it's completely smooth up to all boundaries and corners. Right now, why is complete smoothness, including at the corners, so interesting? Well, it means that you have you don't have any sort of mysterious regimes where there's some sort of odd discontinuity. It means that things are behaving extremely regularly. And even at these sort of new faces, r equals 0 faces, there's a good Taylor series expansion. So what happens is at these faces r equals 0, where theta is varying between 0 and pi over 2, you have a full set of coefficients, which are functions of theta, which are completely determined by the Taylor coefficients of phi naught and u naught, for example. Okay, well, I won't belabor the point, but this is kind of at the heart of what I'll be talking about momentarily. Okay, well, back to this flow of networks. Let me say a few of the highlights. And again, many people have done many excellent papers. But so there was a famous paper of Mandagazza, Novaga, and Tortorelli in 2003, where they were still looking at regular vertices, so meeting in 2 pi over 3 angles, but they didn't insist on the compatibility conditions. And then one has to use sort of a delicate approximation argument, and that's rather technical to overcome. So a work which I'll talk about in just a moment, I did with a former PhD student, Mariel Saez. We classified the expanding self-similar solutions. So these are the things that are model solutions that sort of model exactly what happens when you have many vertices, many edges coming together at a vertex. I'll have a picture of that on the next page. And then using these model solutions, there were a couple of papers, one by Ilman and Nevis and Schulze, where they have this, I call a semi-weak formulation. I mean, they have, PDE solutions, but they use an approximation technique to prove things. And then a recent paper of mine, which actually we'd started writing, 10 years earlier, and it just took a long time to get our acts together. But where we have short time existence coming out of irregular vertices. And so I want to concentrate on this because it has an interesting geometric idea, which I think is more broadly applicable. So first of all, what are these self-similar expanders? Well, if I start off with just straight lines, a system of straight rays coming out of the origin, and so I sort of missed the piece of my computer software where I could sort of make lines look absolutely straight, but so these are a little bit wobbly, but on the left, those are supposed to be straight lines. So I have a system of rays, infinite rays coming out of the origin. I want to sort of flow that forward, and I want a solution which is self-similar, which means that its value at any 2 points of time are just dilations of one another. Now, again, we're expecting things to become regular instantaneously. So this is kind of the geometric picture I want to convey, is that this irregular vertex at the origin has to all of a sudden explode into a cluster of regular vertices. And that's really my interest, is how does that happen? So I have this irregular vertex, and all of a sudden it just breaks apart into this cluster of regular vertices. So self-similar means exactly that. The network for various times of t just look like dilates of the network at time 1. And it has the property that it somehow scrunches down to just the system of rays as time goes to 0. Okay, so it changes topology at time 0, but for all other values of time, they're just dilates of one another. And so, as is well known in this business, anytime you have a self-similar thing, it satisfies a dimensionally reduced equation. So it satisfies an equation in one lower dimension. So in this case, just a one-dimensional equation. And it turns out it's just the geodesic equation, but not for the Euclidean metric, but for this other funny conformally related metric. Okay. And okay, well, that seems a bit weird, but if one has a certain geometric frame of mind, this is actually a very useful observation. So this strange metric, e to the x squared plus y squared times the Euclidean metric, is negatively curved, and it's some sort of version of the Poincare plane. I mean, it has variable curvature, but this is sort of a way that you might picture it. That so it looks like it sort of naturally should be thought of as not the plane, but is just a disk. So this is like the Poincare disk model of hyperbolic space. And the geodesics on it are curves that sort of start from any point on the boundary and go to any other point on the boundary. So there's a certain interesting convexity of geodesics, and there are diagonals that go straight across, which are shortest paths, but all of these other curves are also geodesics, and they can be very thin. They start at one point, they go way in and they go way out again, or they can sort of go bend more gently. And so what we're really looking for is that if we look at time 1 for these self-similar expanders, what I get is a Steiner tree, so just a combinatorial object, but where every edge is exactly one of these geodesic segments. Okay, some of them go out to infinity, so this circle at infinity is supposed to be really infinitely far out in the plane. And you can think of the problem then as the following thing. I have k rays leaving the origin. They determine k points at infinity. So I have like a circle and I have k marked points on it. And then I'm trying to fill that in with a network of curves. And my demand is that all of those curves be geodesics for this funny metric, and that they meet in 3s at 120 degrees. So that's what I'm looking for. And this is a so-called Steiner tree. Okay. Now, one of the interesting things is that there's extreme non-uniqueness. So here I have 4 points and I've filled it in 2 different ways. You can find examples of this with any number of points for k greater than 3, so 4, 5, 6, and so on. There are many trees. And in fact, I asked my local combinatorial experts, I have a colleague, Jacob Fox, who's a really great combinatorist, and I asked him, so this surely must be studied if you have just Steiner trees with, given boundary points. Let's suppose we're just in the ordinary Euclidean disk. I put k points in the boundary and I want to fill it in with straight line segments meeting at 120 degrees. That's a nice combinatorial problem. How many solutions are there for a given k? And he sort of hems and haws and he says, well, there's a bit known about that. Anyway, the answer is it's huge, right? So it's one of these things where if you have k vertices, I don't know, he said the answer was something like, k factorial to the k factorial to the k factorial. I don't know, it's some enormous number of solutions. Maybe I'm exaggerating that a bit, but there's extreme non-uniqueness. Okay, there's a finite number of solutions, but it's very, very big when k is not just 3, 4, 5. Okay, so how does this apply for short-time existence? So I just want to get back to this PDE problem. So if I start with an irregular network, and I'd like to show that it flows for a little while, the phenomenon I'm very interested in is how do these irregular vertices explode into regular vertices? Okay, and so the answer is that, well, if you just have trivalent vertices, even without, well, let's say if the compatibility conditions are satisfied, then it's really just a standard parabolic problem. You have strong continuity to semigroup, and the network just flows. It's a nice solution to the PDE with boundary conditions, so there's no problem. You can work in some fixed space, C1 alpha, C2 alpha, whatever. If the compatibility conditions are not satisfied, then you again have to use an approximation scheme. And so it doesn't really tell you, this approximation scheme doesn't really tell you exactly how the compatibility conditions are instantaneously popping into existence when time becomes positive. And for irregular vertices, something even more dramatic happens. It's not just like the compatibility conditions are being satisfied instantaneously, but in fact, these new vertices are being created. Okay, so this is the thing that we tried to understand from a certain point of view of a subject for called geometric microlocal analysis. And the philosophy of this, which I'll get to in the next page, is that, well, first of all, we're expecting that if we have all of these parameterized arcs at time 0, in each parameterization, there's going to be some weird singularity at t equals x equals 0, namely at the vertices, right? But this is in the domain space. So t equals x equals 0 means on the incoming part of the parameterization. And in the image space, R2, and then I want to keep track of the time parameter at the same time, you expect some sort of strange behavior to be happening at the vertices at time 0. So we're trying to resolve each of these two things. And as, again, I've described before in other things, I expect to have sort of several curves meeting at a point at time 0, and then they instantaneously resolve into a bunch of regular vertices. These are marked by blue dots on the right-hand side. Okay, so an irregular vertex explodes into a cluster of regular vertices. And so here's the key idea, and it's a bit of a weird one if you're not used to this thing, but I already gave you a warm-up to it, which is that you introduce these parabolic polar coordinates. And so this is a process of blow-up, and again, I think that mathematicians have been doing this forever. You introduce singular coordinates and it makes the problem look simpler. This is just introducing singular coordinates and then taking them seriously from a geometric point of view. So on the left-hand side, I blow up at t equals x equals 0, and I create a new r equals 0 face, rho equals 0 face. So this is kind of a new interface that kind of intermediates between the behavior along the positive t-axis and the positive x-axis. So it gives room for some sort of transition of behavior between what's happening in the two faces. On the right-hand side, I have the domains, the range space, where I have all the curves coming in. The vertical is time. So I'm just, if I look at various height surfaces, if I slice at t equals 5, I get the network at time 5. And what I do is I blow up at the origin at time t equals 0, or at the vertex at time t equals 0. And geometrically, what that means is I'm sort of creating a little bubble which takes the vertex and it blows it up into a circle. And what that means is that these various curves that are coming in no longer intersect. They just intersect the boundary of the circle. So I'm just separating out the various directions of incoming approach. And so here's what I expect. Here's the picture from a non-blown up picture. So I start at time 0. This is the bottom slice. And I have the irregular vertex with 4 things coming together. And so I didn't dare draw this because it would clutter it up with too many lines. But if I take a slice with a t equals 1, for example, what I'm going to get is something where there's one extra new curve in the middle, right? So it's this bad vertex at time 0 has sort of split apart into 2 vertices. And this is what it looks like in space-time. Now, here's what it looks like. Now, this is a worse picture, and I tried to do my best. And again, apologies for my bad art. But this is what it looks like in the blown up picture. So I have the yellow curves at time 0, which are meeting the boundary of the surface, but they're separated out. On the bubble itself, at this capital R equals 0, I have a network of curves. And as I'm going to explain what that thing actually is from a geometric point of view, is one of these expanding self-similar solutions. So this bubble looks like a copy of R2, and I just plonk on it one of these self-similar solutions. And then out of each one of these arcs, I have a nice evolution. So this is really the picture that kind of is supposed to explain things, is that it says that once I've passed these sort of singular coordinates or this sort of weird new geometric space, everything is looking very smooth. This looks like a more complicated picture, but everything has a nice Taylor series. And so the way that I do this from an analytic point of view is I introduce these new singular coordinates. So in the domain space, I have S and tau, X over root T and root T. And the range space, I have Z over root T and root T. And so that means that the curves gamma J are going to be replaced by 1 over root T times gamma J. Okay. And then I'm going to, I've introduced a new coordinate system, and the equation looks more complicated. So here's what the equation looks like for the jth curve. And I want to make a few observations. So the equation looks a little bit worse, but not too much worse. The right-hand side, actually, this nonlinear bit doesn't look bad at all for interesting reasons. But the left-hand side with the TDT has become a little bit more complicated. So one thing to be very conscious of is that this region, that the d by dt term in the equation in these singular coordinates has become a tau d by d tau. Okay, and that's a well, how can I say, that's a degenerate parabolic thing. If I introduce t hat, which is log tau, then it's really just d by dt hat. But the big change now is that tau going to 0 is the same as t hat going to minus infinity. So what that means geometrically is that if I go back to this picture, as I approach the front face, the equation is sort of parabolic at the bottom faces, where t was 0, but at this weird bubble, it's like time going to minus infinity. So this change of coordinates is virtually like time going to minus infinity at that bubble. Okay, and so as I say, the real yoga of geometric microlocal analysis is that you just demand, or you hope, or you expect that everything that you're looking for is smooth. That's a little bit of an overstatement, but you assume that it has a good expansion. And, that's what we all hope for, that things behave nicely. Real life doesn't always work out that way. But in fact, in a remarkable range of problems. Yeah, please.
So, but what I don't understand somehow, you have different solutions for these curves of this bubble.
Yes, so you choose one of the expanders. You have this big one,
but in principle, you have a freedom of choosing any of these.
So that's right. So if you have, 5 irregular vertices, at each one you make a choice, right? And you have a finite choice at each point, and then that determines what happens afterwards. That's 100% correct. Okay. Anyway, so the point is you hope for the best. You assume that everything has an expansion, and you start trying to construct it. And so let me just give you a brief rundown on what you do. You just hope that this solution eta has an expansion, a power series. You plug it into the equation, and what you're going to get is the following equation. So on this bottom line here, on the left, what happens for the leading term, it's a nonlinear equation for eta naught. And that equation is exactly the geodesic equation it's exactly the self-similar expander equation. So what it says is that if you're going to assume that this has an expansion, then the only possible thing you could put in as the leading coefficient is one of these self-similar expanders. That is the unique initial condition. Of course, there's a finite number of choices, but you have to put that in. And then the second equation on the bottom says that once you've chosen that bottom guy, then you're going to have a inhomogeneous equation. So this notation of this big square brackets with the sub L says, I take this nonlinear expression and take the Lth term in its Taylor series. Okay, so so this looks like a linear equation for eta L with a bunch of inhomogeneous stuff coming from eta 0 through eta L minus 1, and you solve those inductively. So the moral of this, even if you don't follow this, is that eta 0 just has to be a self-similar expander, and all the higher eta L's are determined from that inductively by just solving an ODE. Okay, so there's, getting this ODE right and keeping track of everything. These eta L's have a part that looks like a polynomial of degree L plus 1 plus a rapidly decaying piece. And the point is that the various boundary conditions determine exactly what these solutions have to look like. So there's a well-defined inductive procedure. Once I've chosen eta naught, then everything else is determined by it. And the upshot of this discussion is that you've constructed a Taylor series. So you've just sort of found a formal solution of this problem. So what does that do for you geometrically analytically? Well, it means I can construct an evolving network, which has all the complexity of these exploding vertices, right? But if I plug it into the nonlinear equation, so I have to summarize this as a script n of gamma of t, I get something which is not exactly 0, but it vanishes rapidly as t goes to 0. So I found a solution to all orders at t equals 0, but I could only do that by introducing this weird geometry. Then I use fairly standard PDE methods to sort of construct the remainder term. What you want to show is that I can kill the right-hand side by adding a term which also vanishes rapidly. Okay, so this is, again, not very surprising that one can do, but I'll omit the details. So the advantages of the approach is that it gives you incredibly strong pointwise behavior. You just know exactly what's happening sort of up to all derivatives at all boundary faces. Understanding initial networks with lower regularity is a matter of approximation, so that's not so hard. And it also really quantifies the non-uniqueness at each stage. Okay, so so I want to mention a couple of other problems. Since I'm getting really at the end of my period, let me just say a few things rather quickly. So what about foams of surfaces? So this whole approach has not been carried out yet, but let's just say there's no reason it shouldn't except for just working harder. It's a bit more complicated because it's two-dimensional instead of one-dimensional. There are sort of more classical approaches. So I feel like Schulte and Brian White have studied triple junctions of surfaces, where you have 3 surfaces coming together in a curve. There's work which I've been talking with Schulte and Edelin about how do you evolve tetrahedral singularities. These are, again, by these kind of older PD methods that don't sort of take into account this sort of fine regularity properties. What's missing from doing sort of this more elaborate approach that I'm just discussing is classifying the self-similar expanders. So this story that I told you about these geodesics in this funny space, there's an analog of what one should do, but you don't have a good existence theorem for those yet. So that's what's missing. But I expect that to work. And, you know, now, I have a small extra section, which I think I'm probably going to skip altogether, but just to say that there's a very similar thing, but where you have to deal with the analysis in a bit more direct of a way when you're trying to evolve what's happening on a surface of conic singularities. And let me just give you a couple of highlights. So forgive me, I'm skipping a lot of details here, but you're trying to evolve to a constant curvature metric. And let me just write down the equation that you're trying to solve. So there it is at the bottom there. You have a function u, and you're trying to solve a limiting porous medium equation. So dt of u is Laplacian of log of u. And the complicated thing is that the Laplacian, I can write out in coordinates here, is singular. So this is the Laplacian in polar coordinates, but it has some features which make it really a singular problem. And what's really at the heart of making this work is that you identify a regularity theorem. And let me just state what it is in the elliptic world. It says if you have a function which is twice differentiable, its Laplacian is, you know, let's say Holder continuous of order beta, then actually U has the beginnings of an asymptotic expansion. So it's not that it has a full Taylor series, because the right-hand side is not regular, but it has a Taylor series to order 2 and some remainder term which you can't control very well, except for that it vanishes at some rate. So this is very much like the classical Friedrichs construction for domains, which is adapted to the Holder setting. And sort of the big discovery here was that this Friedrichs domain actually evolved. So you can actually make the heat semigroup flow that domain. So and that's really the thing I wanted to say here is that this is a finer regularity result, but you've identified a core domain for this operator, which is kind of a complicated thing. And then you show sort of by very sort of delicate arguments that actually propagates under the heat flow. Okay, well, forgive me for going over time, and I don't want to say too much more, except just to give you a couple of morals. One is that choosing the right function space is very delicate and really central to this whole thing. So I think that too many of us get bound up in saying, well, I'm just going to use the classical function spaces. And you can do that, but you'd usually be making a big mistake simply because the right way to phrase regularity involves function spaces that encode sort of different types of degeneracies. And once you phrase things in terms of the correct function spaces, you have a much stronger theorem. Uniqueness, when you start with singular objects, is rare. So you expect strong degrees of non-uniqueness, and there is a good sense of maximal regularity, but it's often phrased in terms of these kind of unusual function spaces. Okay, so again, this generalizes to higher dimensions, much more complicated interfaces and so on, but I think this is a very promising area of study, and I think I will end there. Thank you very much for your attention.
Thank you very much, Rafe, for this very interesting talk. There were a lot of different issues you addressed, so I can imagine there are several questions or comments.
So
Yes, please.
maybe I can ask. So is it concerning these vertex conditions? Yes, you for example, in the case of 3, then you enforce the angle 2 pi over 3.
Yes.
But you see, if I understand this system somehow, one should think that one of these curves can draw this vertex a little bit stronger than the others.
So that's, I mean, so there are many variants. So let me say 2 things to respond to that. One is that, you know, if you sort of demand that the vertices become regular, then of course what can happen is the edges can shrink and that you have regular vertices coalescing into irregular vertices, right? And we saw with that movie. But another issue, which may be related to what you're saying, is that I could actually start with 4, you know, I could start with 4 curves coming together that are balanced, let's say already at time 0. It's an unstable configuration, but there actually is a flow which keeps the 4 meeting with the angles summing to 0. So it's like, you know, flowing and you're staying right at the unstable equilibrium. So, and it is possible to find solutions like that. Obviously, they're not generic. That's
but I was thinking that you wrote this condition that the sum of the directions, so to say, is 0.
Yes.
But why not to write it that the sum of the vectors is 0? Because this would be like
no, and so there are weighted versions of this, and that's 100% right. There are, you know, infinitely many, you know, anisotropic versions of this that you can do. So this is sort of the isotropic version where you demand that the geometric directions add up to 0. But indeed, as you say, you can have some edges weighted by, you know, by different.
Not weighted, but somehow. But it, you see, if you have two vertices, yes, and this curve is almost straight, then it will not change, yes. But if there is a curve which is somehow very curved, yes, then somehow when you try to push it, it will be straight. Probably it will try to push apart these vertices.
Yeah, but I mean, I think that, so maybe I'm misinterpreting what you're saying a little bit, but on the one hand, there are parameter dependent flows. And then this is a parameter independent one, right? Where the curvature really, you know, how big the curvature is as you come there really is affecting how much the vertex moves. And that's kind of the point, is that each individual edge is really pulling it in different directions, but then the boundary condition is sort of binding it together.
Yeah, but with these conditions, it's they pull it in different directions with the same force, so to say.
Well, no, because it's the parabolic equation which is driving how they're pulled apart, and the boundary conditions are telling you that they're getting pulled, but they're not breaking. I mean, I think that probably if we argue a different way, you would be right, but let's say.
No, I'm not saying that I'm right. I want to understand.
No, I mean, I guess my intuition is that the driving caused by sort of how curved each edge is coming from the parabolic equation itself, and that you have this sort of parameter independent condition at the vertex which prevents it from pulling apart. But there are many other things. I mean, you know, there are many models, and you know, there certainly could be one which, as you say, sort of incorporates something that puts the curvature into the sort of the boundary condition in a way. And I'm, you know, people have investigated all sorts of things, and that may well be studied. I'm not aware of it, but
so and what is the physical picture of this? What is it modeling this?
Well, so I mean, one of the original things was if you have a multi-phase grain bound, so suppose you have several things, suppose you have three things, oil, water, and
I see. Okay.
something else, and they're all kind of, mixing and evolving. And the point is that they're trying to stay in some sort of equilibrium. So it's sort of a multi-phase situation. And so I think that's the most compelling model of this. I mean, there are many models out of superconductivity in physics where you see this. There's sort of this whole world of Ginzburg-Landau, Allen-Kahn equation. So there are many different models, but I think that's kind of the most natural one. Yeah, three miscible fluids.
Other questions? Yeah, so something maybe related to Pavel's question. So, I mean, if everything here were completely linear and just you were just taking the very simple heat equation on objects that do not move, then you would have to replace your vertex conditions by something like, okay, you have continuity, and then replace your nonlinear condition by some kind of Kirchhoff condition, right?
Mm-hmm.
And there is a reason for doing so, because on an operator theoretical level, this guarantees that your operator is self-adjoint and well dissipating.
Right. Exactly. Yeah. Exactly.
What is the key word in your settings or in your kind of analysis? What kind of operator theoretical properties are guaranteed by your choice of boundary conditions? And is there a replacement for this kind of vertex conditions that would still enforce the same operator theoretical property?
Yeah. Okay. So that's an interesting question, and of course, there's this whole other world about doing analysis on networks, which many of you are, great experts on. Which is that, for example, you can look at an evolution on a network where you're not thinking the network is moving, but you have some evolving things. So you can think about some scalar or vector valued objects or some sort of quantum graph type problem, right? And then you have these Kirchhoff type conditions at the boundary, which are some sort of at the vertices. And you can phrase this quite generally as that you have you take the Cauchy, if you have a second order operator, like you have the Laplacian along each edge, then you take the Cauchy, the Cauchy data at each vertex, and then you have some big vector space, and you choose a Lagrangian inside of that, and you get a self-adjoint boundary problem, right? So that's a kind of a familiar framework, phrased maybe a little bit more generally, but that's these boundary conditions are really geared towards the geometric application, and the only advantage of them is that they're they're elliptic boundary conditions. They satisfy the Lopatinsky-Shapiro condition. So, and as just actually in Pavel's question before, there's a lot of flexibility you can do. So they're not self-adjoint, and I mean, actually, I don't know, maybe they are, but that self-adjointness is not the feature. We're not using that. And in fact, you can think about, suppose you're thinking about the operator theoretic aspects of this. You can prove, and in fact, I did so that, that the corresponding linearization is sectorial and one has sort of good stability properties. So, but you can only make sense of that sectoriality once you're in the regular framework. I mean, this transition from an irregular to a regular vertex in this sort of weird setting where you do these blowups, you can actually sort of make sense of sectoriality in an extended setting. But so, with these boundary conditions, you have something whose L infinity or whose Holder spectrum is contained in a half space. In fact, in a sector, and one can apply those sort of standard tools. And that's really kind of we don't phrase it that way, but that's really what's going on here. Okay. But we're not taking advantage of self-adjointness per se, and it may not be true for these particular boundary conditions.
Self-adjointness then would be in which space, by the way?
Well, I mean, you can only talk about self-adjointness in L2, right? So.
Yeah, sure. But, sure. But you were saying before that you have to be very careful with the choice of your space. So I guess L2 is probably not the smartest way to.
Yeah, so that's exactly right. Is that you may start, and very often with all these things, as you guys all know, is that you may have sort of a nice L2 theory where you talk about self-adjointness and so on, and you have good spectral control. But then for reasons of the nonlinear operator and so on, you need to move to some other space, some LP or WKP or a Holder space or whatever. And then, of course, how do the spectra relate? And that's not a very obvious story in any case. In this one-dimensional setting, it's not so hard to figure out. But in higher dimensions, it's actually much more subtle. I mean, maybe there's good tools for this, which I'm not aware of, and I'd love to know because I've been thinking about these things. How do you pass from L2 to L infinity spectra, sort of in general? And that's not an easy question, I don't think, and it depends on so many specifics.
Well, I mean, if you have if everything is linear, then Gaussian estimates are typical tool.
Yeah, I mean, those give you some information. That's 100% right. Sure,
Yeah.
sure.
Okay, let me see if there are further questions.
Okay. If there are no other questions, I have another question.
Okay,
But,
good. Thank you.
You show this picture in 2 dimensions, yes?
Yeah.
So what happens if we consider curves in 3 dimensions? Then
that's okay. That's a really
basically
great
will be
question.
4 curves coming together, yes?
Yep. That's exactly right. So in fact, you can phrase all of these questions for k-dimensional submanifolds in Rn, and as you say, the sort of the simplest thing to think about is like curves in R3, for example. So in terms of short time existence, in fact, there's a very similar story. I mean, not all the details have been written down, but you have a notion of regularity of a vertex, which, as you say, 4 can come together in a tetrahedral singularity. And if you have a more complicated arrangement, then it's going to break apart into a bunch of tetrahedral singularities. And that actually is not so hard to generalize from what I've done. So that's quite a tractable story. But there are a lot of interesting physics. So suppose you take 2-dimensional surfaces in R4, and there's a notion of something called Lagrangian mean curvature flow, which is very important in modern theoretical physics and mirror symmetry and so on. So you have these Lagrangian surfaces flowing around. So they're half-dimensional in R4. Now, the simplest thing is that they're just moving around and they don't intersect, but they can easily sort of come together and intersect, or you can have complicated foams of these Lagrangians in R4, and then you're interested in what happens, how did they resolve themselves? So in fact, that's an extremely interesting and timely question that, I'd say a lot of people are thinking about from various points of view.
But in 3 dimensions, you will have 4 vertices of degree 4. Then, yes?
Yeah, for example, you could have, you could either have 3 guys together, which would be kind of very unstable, or the more stable thing is you have 4. You have 6 coming together. So forgive me, you have 4 coming together. So 1, 2, 3, 4, right? Like along the edges of a cone over a tetrahedron. That's exactly right.
Yeah, but these should break sometime, because you see, I don't remember in which dimension, but something like in 7 dimensions, there are no vectors that will have the same angles.
Well, and this is again part of the non-uniqueness, right? So if you think about the following thing, suppose you have 2 curves crossing in R3. Even in R2, you can think about the following thing, right? Suppose you have 2 curves crossing in R2. One possibility is that they can sort of break apart one way, or they could break apart the other way and just cleanly separate, right?
Yeah.
Similarly, if you have like 2 curves meeting in R3, right, they can either just move off of each other, so they still stay nice curves, but they could become like skew, or they can sort of, break into 2 components.
Yeah. No, but see, we were speaking, so what is the most natural component? In 2 dimensions, these are 3 with the angle 2 pi over 3. In 3 dimensions, this will be 4 connected with this tetrahedron. But in several dimensions, I don't know, something like 5. Yes, it breaks. So you cannot find one-dimensional vectors that have the same angles that balance.
Yeah, it's just certain lattices on the sphere. When do you have these regular regular things on the sphere? That's 100% correct. Yeah, that's 100% correct. So I mean, that's an interesting question. What happens? I have no idea, but I think that I mean, you have Euclidean solids. I mean, you have regular solids in every dimension, and so you can sort of introduce symmetry groups associated.
Yeah, but they have too many vectors.
Yeah, no, I understand what you mean. Anyway, that's a fascinating question. I've never thought about that, but actually, that seems like a really interesting one.
No, it's very physical problem because they work only in 3 dimensions.
No, that's a very interesting. That's a very nice comment.
Other comments? Maybe on YouTube, Harun?
But this Harun should tell us, probably.
Yeah, this is...
Yep, nothing on YouTube.
So this will come tomorrow.
Okay, well, thanks everybody. That was really very kind of the invitation. And
thank you so much. Yeah.
Very interesting. And well, have a nice day.
Yes,
web
now I
just
got my day
started,
ahead.
Yeah.
Okay.
Okay, so thank you, Rafe.
Thanks a lot for a very interesting talk. It made me think. It's a new world for me. So
Good.
new perspective, let's say like this.